I've forgotten exactly how we got to this point, but
you were talking about SR and the speed of light.
Yeah, indeed, and maybe the non-constancy of it. And I just referred to a little analysis I had done about the original Romer observations, but I didn't have any visual aids, and so it mightn't have come over very clearly. So I just sat down for an hour or so and just made out 3 slides or something. And I have all the data in my head, so I haven't actually put them on the slide, but I'll show you the principle. So Romer's observations of Jupiter's satellite, Io. Io is the nearest satellite of Jupiter. It was discovered by Galileo in 1610, and it actually has been the subject of very extensive astronomical observation for hundreds of years. I think it basically started in the Paris Observatory under Cassini, the Italian astronomer, who was the director of it, where they were endeavoring to use the timing of the eclipse of Io to determine the longitude of a location. They were offered actually a lot of money by the king, the Sun King, Louis XIV. And so I think that resulted in a gentleman by the name of Picard being hired, and he was sent to the old observatory of Tycho Brahe, just outside Copenhagen, then, and to pick up some of the observations, that
let me stop you here, Ian. Okay, so the idea was that the motion of Io around Jupiter is like a clock, and you can use that as a clock that's a universal clock to determine what time it is, and from knowing the time you can determine your longitude.
Yeah. Now, obviously that's not specifically what I'm going to be talking about. I'm talking about the measurement of the speed of light. But that's
what the measurements were about. The project. Yeah. That was the motivation.
And they were actually not very successful because it was overtaken by other means. I think that the timepiece of Harrison in England really, was the answer to that. But anyway, so but the interesting thing about Romer is that this Picard gentleman, there was a youngster who had just completed his, I suppose, 3rd level studies, Olu Romer, and he became an assistant to this Picard, and he was so impressed with him, he said, I'll bring you back to Paris with me. So Romer started working in Paris, and he performed a lot of the work. Now, so he went a bit further. Let me see. Yeah, and by the way, I've just underlined observations because I'm claiming that what you see in the textbooks is just the first set of observations. They don't talk about the second set, because the second set, well, I'm being a bit conspiratorial now, admittedly. The second set is rather embarrassing. If you look at it, it might be contradicting the theory of relativity, for example. Anyway, so here's the first set of observations, which the details are given in the textbooks. Syzygy is a nice word of Greek origin, which just means yoking or united. So something is in syzygy when they're in a line. So, for example, the Earth, Sun, and a planet. Okay. So you can probably see my cursor here. Can you?
Yes.
Okay. So obviously this is well known. When the Earth is on the same side of the Sun as Jupiter, you do observations. Actually, looking at this in very, very great detail, I think you'd have to be a little bit off the 0 degrees there, because Jupiter would be too near the Sun to see it. So there are slight errors in the observations here. But anyway, you do it when it's in syzygy, when the angle between the Sun, Earth, and Jupiter is 0 degrees. And then you do it when it's 180 degrees. So in other words, when the Earth is at the other side. Here's the Sun in the middle. It's not shown. Okay. And these were observations. Again, there are complications that only for a certain number of months of the year can you actually see the moon being eclipsed, because the eclipse occurs when the moon enters into the shadow caused by Jupiter from the sun, and then it emerges when it emerges out of the shadow. But at certain times, in fact, for I don't know, many months of the year, it is occluded by the disk of Jupiter from the position of observation of the Earth before it gets into eclipse. So, you know, you don't have all the time of the year to do these observations. But anyway, we have an idealized observation roughly around syzygy, union. And these are 1673. D is the diameter of the Earth's orbit. So, what Romer found was that they'd had very detailed observations, basically from Cassini, going back many, many years, about the duration of the eclipse itself. They got it to about 42 and a half hours. And the timing and when it should appear and disappear and so on. And he found that relative to 0 degrees angle subtending and 180 degrees subtending, there was about a 22-minute delay. So now remember, the idea was maybe that the speed of light was instantaneous. He said if light,
a 22-minute delay of what?
So in other words, the time. Say you take the beginning of the eclipse. You could do the end as well. When as soon as the satellite enters the shadow of Jupiter. Now they had that all timed to a T, and it would occur about 22 minutes later when you were on the far side of the sun than were you on the near side. Okay. So how can that be explained? It might have been experimental error. Well, what's his name? Romer got the idea that if the speed of light was finite, that could represent the time, the extra distance it had to travel, the one Earth diameter. Okay? So if D is the diameter of the Earth's orbit, and if that reason is correct, by the way, I'm just keeping the zero C0 terminology because I was using epsilon naught and mu naught, and I'm just talking about vacuum situations. But anyway, so C0 is the speed of light is equal to, if he's right, the diameter of the Earth over that difference in time, which is 22 minutes. Okay. Now, if you do that, obviously they didn't have as accurate values. But so, for example, if you say the diameter of the Earth is something like 186 million miles, just keep it in miles, and then the delta T minus, I'm calling it, and that'll become clear maybe in my next slide or two, is 22 minutes. You get something like 155,000 miles per second. So it's a little short. It's of the modern value, but it's of the right order. You know, it's maybe 20% too low or something. And interesting enough, Cassini didn't accept this actually himself, the boss, who had all these calculations done for years. But there were people who supported, actually, Edmund Halley and also Isaac Newton supported it. And they used it because Newton had originally used the proposition of an infinite speed of light, but he then modified it to this value. And actually, strangely enough, Newton seems to have a more correct value because the delay shouldn't be 22 minutes. It should be about 17. It's actually 16.6 because it's 8.3 minutes from the sun to the Earth multiplied by 2 for the diameter. So he overestimated that a little. Now, there was another set of observations which were actually crucial because it was important to get the true period of the eclipse. So, without any of these distractions, you know, about occlusion or being on different different sides and so on. So from the immersion and emergence of the Io from the shadow and so on, to go right around, as I say, about 40, just under 42 and a half hours. We call that T0, okay? And by the way, I did talk earlier about the difficulty of doing a lot of these measurements, and you'll see this maybe in the next slide. What Romer did is he did multiple observations, because one observation and another one, they were giving different values. So he would do maybe 30 observations and he would average them, and we'd get 42 hours, 29 minutes, 28 seconds or something would be the T0, okay? So, any more questions on that before I go to the next slide? We can come back to it if you wish. Now, but this is the operative point. So these are the next set of observations. They were done over a number of years, and it was in 1676 that he published these from notebooks. We call these the quadrature observations. Syzygy is when they're in line. Quadrature is when they're at a 90-degree angle. So if you take the Earth and the Sun and Jupiter to be, so the Earth is at quadrature there and there. Actually, it's at positive quadrature there. So in other words, I said 0 degrees, 180 degrees Kelvin. This is 90 degrees, or pi over 2 radians. It's at positive quadrature there because the Earth is moving towards Jupiter. And it's at negative quadrature here, which is minus pi over 2, or it could be 3 pi over 2. In other words, 270 degrees, if you take the radius vector as being the positive x direction. So here's Jupiter, and here's Io going around it, okay? And these would be the syzygy positions, E and H. Now, so I've analysed this a bit differently. I've got a similar result to some of the other analysis, but anyway, for what it's worth, I'll give you my analysis. So, my cursor's going. So, this is obviously exaggerated in scale, but the Earth is moving from F to G. And sorry, I've gone, and it's moving from L to K. Now, so what he actually found is very, very small differences in the timing of the eclipse, which was known pretty accurately when it was in positive and negative quadrature. So when it was in positive quadrature, the eclipses seemed to occur a little too early, maybe up to 3.5 minutes too early. And when it was in negative quadrature, they were appearing maybe about 3.5 minutes too late. Or it was very, very varied values of these, and that's why he had to take multiple readings and average them out. But so again, he got the brilliant idea, which again was rejected initially by Cassini, that if the Earth were moving towards the ray of light coming from, the Sun reflecting off Io just before it had been eclipsed, well, then it would take less time because you're moving towards the thing. The speed of light should be c minus v. So, so it's a bit like, you remember, that's why I call it delta t minus. In the MMX experiment which we were talking about yesterday, you get the sum of the to and fro. It's a two-way speed. Well, the previous slide showed that it was a one-way speed. We were just measuring, we measured a delta t minus, the delta t it took for one condition versus the delta t it took for the other condition. In the previous case, it was going the actual distance of the diameter of the Earth. But in this case, it's actually, well, if you remember the old Sagnac thing is a delta t minus, you're getting the difference between rays going in counter directions. And in the Sagnac experiment, we just had this keeps going, this cursor. We just had we just had L over C naught minus V minus L over C naught plus V. So in other words, here we're going from L to K, so it's C naught plus V, which is a greater quantity, and therefore in the denominator, the whole fraction is a lesser quantity. So the delta t, in other words, the first bit here, it takes a shorter time when the planet is going between F and G than it takes from L to K. So anyway, if you work that out, that's the way I put it down. C naught T naught is the during the T naught cycle. If you multiply that by C naught T naught, you get the distance, the average distance without any V. You see, if V were 0, for example, there, you would get delta T minus equals 0. But so if you and I suppose if the special relativity postulate number 2, as it is normally expressed, were true, well then you shouldn't have C naught minus V. You should have C naught there, and you should have C naught minus C naught again 0. T
Okay,
naught.
I got what you're saying now. I knew you were driving at that.
Yeah. You're with me, which is good. Yeah. Okay. I'm going into too much detail, but
Yes.
and sometimes you're with me. Others are.
Was this
Jerry,
before,
you got a point.
was this before the constancy of the velocity of light was introduced? They thought it might, before that was considered. Maybe they hadn't taken that into account.
Yeah, that had never been considered. But remember that it had been considered that the speed of light was infinite, perhaps up to this. This is fairly revelatory. And actually, it was measured. The next time it was measured terrestrially was a two-way speed by Fizeau in the middle of the 19th century. But this is actually more accurate. This is at the end of the 17th century. So it wasn't until actually Albert Michelson himself, with his interferometer, did observations that they increased the accuracy very much. So all you do is, if you accept those equations just for the moment, just do a bit of algebra, and interestingly enough, C naught equals 2v T naught over delta T naught. V is the speed of the Earth, as they say. T naught is the period of delta T naught. Now, I put approximately equal because, interestingly enough, the gamma factor comes in there. It's actually 2v gamma squared, I think, T naught over delta T, if you just do the algebra. But, and we could work it out. We get a sort of a quadratic or a biquadratic and so on. But gamma squared is approximately 1 because V is the 1/10,000th of the speed of light. So it's a very, very small quantity. So it's the same as in the Sagnac experiment, basically, although the speed here is a bit greater. Now, so let's say V, I'm just keeping to the old imperial units because we're just used to them every day. V is about 18 miles a second, and T naught is about 42.5 hours. Now, delta T minus, I think maybe the average could have been as much as 7 minutes. Well, anyway, if you plug those values in, you get again a similar value to C naught, as I've just said, about 155,000 miles per second, a little lower than what is.
Well, I would say the previous diagram of the observations were much more effective than the one that was just shown there.
Why so?
Well, because it showed instead of like from side to side, like they're almost sort of equal, not really equal, but more equal than like the distance across from Earth to Jupiter from one side of the orbital to the other. And
yeah, well, you're right. I would say in this regard that those are pretty definitive. They did a number of observations which were at favourable times, and he was getting this 22 minutes, roughly so. Now, in this case, the differences were very much smaller. They were only minutes at the most. In fact, I think in some cases they were getting practically zero difference, which meant that the speed of light was infinite or something, and they were getting seconds and so on. So what he did is, I think for these set of observations, he got 30 orbits of the Io satellite, and he averaged them out, and he got 3.5 minutes or something. So they're very, very much smaller, and therefore the errors would be very much greater. But But they illustrate a principle. I mean, how could you explain? Well, you could do this with modern equipment, and I dare say modern repeats have been done, but I'm not aware of them. But if you did this, or even if you accept these values, because these values are not too far out, they give the correct value of the speed of light, for example, within 20%. How can you explain how this works if the speed of light remains constant, irrespective of the speed of approach of an observing object or the speed of recession of the observing object? If there's no, if C naught plus or minus V equals C naught, this doesn't work. It should be the same on both sides. It's not the same. So, but and the point I'm making, just to bring a bit of conspiracy into it, is you don't see this in the textbooks. You see the other one, which is clear, and they say Romer was brilliant and he just found that and that's the end of it. But actually, these were the next set of observations, which I believe are very pertinent to today's analysis. And we talked yesterday, for example, about putting an MMX thing out into space, and I talked about chipping away. So this is something which was done quite early, which I believe cannot be explained by, it contradicts special relativity, as the Sagnac effect does. So my last slide is this, actually. I'm just being a bit fanciful. One of the things I maintain is that there's no symmetry between source and observer motion, and the relativistic Doppler equations, which are symmetric, are erroneous. I've given the different ones, which are just an extension of classical physics, really. So I've said that the Romer and the Sagnac experiments are analogous. Nobody maybe has thought of this, but regarding Galilean composition of speeds. So if you look at them, just maybe, I don't know if this cursor just goes, and there it is again. If you look at this table just moving around here, and your objects being reflected and effectively circulating, going both ways, clockwise and anti-clockwise and so on, and then coming back. And you look at this thing again as being sort of like an emission of light here, but the observer or the receiver is moving towards it or moving away from it. You get the same equation, delta t minus is proportional to 1 over, well, omega r is v in both cases because it's the tangential speed. And you get the same equations. And the Sagnac experiment has been verified, to 1 in 10 to the power of, 10 or something with modern Mazars and so on equipment. And this thing is not terribly accurate by modern standards, but we certainly believe in the first set of experiments of Romer. Why don't we believe in the second set? So I hope that that's a bit clearer than my exposition last week, which was a bit garbled.
I understand what you're saying. I understand it, and the question is, does anybody else have any questions?
Yeah, good summary, Harry.
I think, well, my personal opinion about what Jim Marston said yesterday, I was going to say this is probably not welcome for me to say this. I don't think there's a need for this flying interferometer experiment, because I think we already know that based on GPS and the Hayfel-Keating and the experiments that we already have, I think we already know that special relativity is wrong. The second postulate is false. So I don't really see that this flying interferometer experiment does anything other than adds to what we already know. And I suspect that if it were to be done, the experts would say, oh, we already knew that, no big deal. We already got that in our theory. That's how they respond to this sort of thing. Anyway, that's my view. But I think this type of knowledge, we already know this. We already know this. And, it's not that we don't already know it, it's that the people who write the textbooks are ignoring it.
Right. They're either ignoring it or they're unaware of it.
Well, I thought the Michelson and Morley experiment, the one on Earth and the one proposed for outer space, was to conclude if there's an ether and possibly detect its position, or maybe just to prove that it exists at all. I didn't know that it had anything to do with the constancy of the velocity of light. I'm unsure.
Yeah, that's a good point. I had a problem with what Jim Marston was saying as another criticism. And my feeling is that people watching it who are relativity proponents would probably say, well, this guy's just trying to prove that an ether exists, and we know that it doesn't, and so we just ignore what he's saying. And that what you said, Jerry, is kind of, it's like you didn't really clearly understand what the point was.
Oh.
I think you just said that. You didn't clearly understand what the point was. Does it have to do with ether, or does it have to do with...
I mean, I haven't ever heard that the intention of the original Michelson and Morley experiment was to discover if light is constant. It was a fortunate side result, as I understand it, though I'm skeptical of that myself, though I thought the original purpose was to detect the ether. That's all.
That's correct.
Yeah, the other bit was put on later, because the SRT said, well, we'll explain this by saying the speed of light is constant in all circumstances.
Right.
Right, yeah.
And so now
I think yesterday, one of the things was, like, some of us who would use this entrained ether business without the Stokes totality of entrainment, because of the or consequent on the spin of the Earth as distinct from the orbit. But if you take this in trade, he said, well, once you're outside the Earth's ether influence, you would get a greater effect. So you get a very small effect in an MMX experiment. The textbooks say zero, but it's not zero. It's maybe an eighth of it or a sixth of it in the original 1887 experiment. And those of us who say, well, that's ether entrainment, if you go outside into outer space, you won't get this entrainment by the Earth, and therefore you should get a full effect. So it would put it up to these orthodox scientists to explain. Now, I agree with Harry. I said it myself yesterday. I'm sure they would come up with some ad hoc explanation, but it would be another maybe slight embarrassment to them. They have to put on their thinking caps.
Assuming the experiment came out in the way desired, but what would happen if they got a null result?
Well, yes, you have to consider that would, if they did, let's say, the scientists would say, well, that proves we're totally right. And
they'd say that's another experiment that proves special relativity is correct, and then, boy, dissidents would have big egg on their faces.
Well, actually, many etherists interpret the alleged null result as a result where wing contraction shorten one side of the interferometer to produce the illusion of a null result. That's what many think, actually.
Yeah. Also, in emission theory, we would predict a null result.
And that Canadian scientist who died a number of years ago, what was his name? He's published in Galilean Electrodynamics, but he did an analysis which claimed to show that there was an additional effect which hadn't been taken into account with rays bouncing off a moving mirror. And if you took that into account, the special theory of relativity should give a positive effect. And if there's a null result, it disproves relativity. Now, I disagreed with that, but that was his... I don't know if you're familiar with that.
I can't remember.
Marmot.
Yes, I think that's who it is. Marmot, yeah.
Yeah.
Yeah. All right. I think we're coming up to we got 8 minutes.
I'll stop sharing my screen now, shall I?
Okay, that was pretty good, Ian. I'm not. I wasn't really aware of this topic that.
Okay, I'm glad to have brought something new to the scene.
I didn't know about it, and so I learned something I didn't know about. Certainly it raises the issue that you raised, which is why we don't hear about this. Um, yeah, that's kind of an interesting.
Well, I was actually aware of the theory, and I read about it years ago. Though I have to admit I was skeptical. Though Ian has brought it more to light to where it seems more of an effective discovery than I once initially thought.
But had you?
Can I ask Ian a question? If you might clarify a bit for us, in your last slide you have source versus observer asymmetry. Now those two words, source and observer, if you could perhaps try to enlighten us a little bit about what those two words refer to in the diagrams that you presented, sir.
Okay, so in my diagrams, I suppose, Jim, the source is the light coming from Jupiter satellite Io. In other words, it's the reflected light from the sun, and the observer is Mr. Romer in his observatory in Paris. Either or being on the opposite side.
Okay, thank you. That helps.
Okay. No, Jerry, I was just wondering, in view of what you just said, that you had some awareness, had you actually seen any publication or any information about the second set of Romer's experiments, the 1676?
I can't recall the details. It might have been the first. It was a very old book.
Yeah, the first is available everywhere, but I had never seen the second lot. And it was brought to my attention in a number of ways.
I was just going to ask you that. How did it come to your attention?
Okay. Well, I think
we only have a few minutes.
Yeah, okay.
6 minutes.
I'll have to give credit to the Italian scientist whom you may have heard of, Roberto Monti. Have you heard of him?
Yes.
Okay, well, I haven't heard from him in recent years, but he's done a lot of work. And funnily enough, his paper was referred to by the very, maybe it wasn't the first, but one of the major lectures I attended of Alf Kelly. It wasn't the first one, but it was one in which I wanted to go up to Kelly and have some words with him. And he referred to this paper. And my colleague, who's since deceased, he went up. There was a long queue. I said, I won't be waiting, I have to go. But he went up, and this man gave me, or I think he either gave me a copy of Monty's paper, The Special Theory of Relativity, a Critical Analysis. But it's actually on the web. You can Google it and you'll get it on the web. And in that paper, he covers a lot of things. He spurred on a lot of ideas from me. So he has a small paragraph on this, the Romer's experiments, and I've just expanded what he did. The germ of the idea was given to me by Monty, and that prompted me to look at the original references as well. So do have a look at that. You know, I didn't dream it out of.
That's interesting.
Pressure.
Okay.
And I didn't actually go to the original.
So this is another guy who's a mainstream kind of scientist who's basically frustrated because he's being ignored by the establishment who want to basically hold on to their belief system.
Yeah, I wouldn't even call it mainstream. I think he seems to be quite revolutionary.
He's mainstream in the sense that he's an academic that's passed gotten to be a member of the club. He may not be a valued member of the club, but he's a member of the club, right?
Yeah, he might have been kicked out a bit because he has been local. But he was at some of these conferences long before I was involved. Like some of these conferences, the one in London on special relativity, and the other one, Galileo back in Italy. There were a few of those about 25 years ago in Italy. And being an Italian, I think he was involved with those. But I haven't heard anything of him in recent years, so I don't know if he's still around or whatever.
That'd be.
He drew this to my attention in the first place. his
I've
paper.
heard of him, but you know, I guess he's one of these people that you know. There's so many. I mean, you have. I mean, I spent years on this whole special relativity thing, and you know, there's so many. There's so much stuff that I've forgotten. You know, there's so much dissident literature out there. There's so much of it that I don't even remember existed anymore. And I went through my computer, you know, pulled out an old backup drive, and I was looking through what I had accumulated on my old computer. And there's all these papers in there, and I open them up, and I go, "Oh, I remember that paper." I mean, it's just to remember the dissident literature is vast and huge, and you know, of course, the Germans I think did the what is it, Geo Rumor project. Um, they amassed a list of all the papers on dissidence to relativity. I think that's the where the database is that has all this stuff, and it's just a large, huge database of people who criticized special relativity and yet made no impact whatsoever.
We might be our own worst enemies to a certain extent, because I believe in succinctness, actually, you know, and if you just, we supply a lot of information. We're not shy in papers and writing, and we're very verbose, and people say, oh, they just turn people off. Whereas if you had something more succinct, you know, because there are a few key points, such as the one we were talking today, and if you maybe put those into a paper or promoted those, you might get a better hearing. There's too much information, I think, out there from the dissident side.
Well, one of the, just to sort of, we're coming up here with 1 minute left. One of the problems is that all of the issues that have come up, you know, Sagnac effect, this came up and was discussed yesterday, DPS, all of these experiments, you know, that come up, there's, for every claim made by an anti-relativity person, there's counter papers that have been put out. So what they do is if you assert special relativity is wrong, some minor guy comes out and says, your paper is wrong and everything in it is wrong. And so what that does is it creates a lot of confusion as to who's right and who's wrong. Okay, and as long as the confusion is kept going, they're fine. Okay, so it's all about perpetuating the confusion, and people
it could be that the actual objective is to create confusion, because you know, there's sort of a technology race among major economic nations and powers, and
it's a bit of a chicken and egg situation. You see, should we be providing more technical information and slowly chip away at the existing incorrect theories, or would it be more beneficial to try to inculcate in people's minds an objectivity and a consideration that the general view...
Recording in progress.
The view generally held may be wrong. You see, most people, whether they're experts or specialists or the populace at large, have ingrained in their minds that what they're being told by experts, by people who are qualified nominally and people in high positions, it's very unlikely to be wrong, and they just accept it.
You're talking about COVID.
I'm talking about COVID and all of us, we're inquiring people. I think David calls it critical people. And maybe that's the way we're built, or we want to believe that. But yeah, that's a good example. Now, the same thing with relativity. And I think no matter how much evidence you give people, if they're not willing to entertain the view that orthodoxy might be wrong, they won't follow you. They won't follow the logic.
Okay, I'm going to lead on to this to talk a little bit about angular momentum. If anybody has any other comments, I'm not going to give a. I'm just going to sort of. I want to sort of tag on to the thought that you were just saying, Ian, which is that in doing a little bit of research, I have this book here about stellar. What's the title of this book? This is a. Um, it's in Italian. It's a course on star evolution. Okay, and and I thought, the problem with this angular momentum problem there, it's a big problem because the idea is that um, stars and galaxies and planets condense from gas clouds. And I just never could make any sense out of this. And the angular momentum problem is, well, if the cloud is static, if it's just a static gas cloud, it's not moving or doing anything, and then gravity collapses it, where does the angular momentum come from? Okay, so there's no angular momentum. So if the cloud is static, no angular momentum. But if you have just a little bit of turbulence, they hypothesize turbulence. So you get a little bit of turbulence, and then what happens is when the cloud condenses to form stars, you get too much angular. Okay, so they have this problem of not enough and too much, right? And so then they have to come up with this excuse of how do we get rid of the too much angular momentum. So there's a lot of theories that have been proposed to do away with that. And this problem has mainly been associated with the formation of the solar system. Okay, so what you have is you have a lot of people who are trying to explain how the planets formed, and then you have other people who are trying to understand how galaxies formed, and other people trying to understand how stars are formed. But they all have the same angular momentum problem and difficulty. And one of the things that surprised me was that in reading this book, it turns out, guess who supposedly is credited according to this guy, Grat, who's an Italian. Guess who he credits the whole origin of the idea that stars and planets originate from gas clouds? Isaac Newton. And supposedly in a letter to Bentley, a frequently quoted passage from Newton's letter to R. Bentley is of great interest to us. If the matter were evenly distributed throughout an infinite space, some of it would convene into one mass and some into another, so as to make an infinite number of great masses scattered great distances from one another throughout all that infinite space. And thus might the sun and fixed stars be formed, supposing the matter were of a lucid nature. I don't know what he means by lucid nature. Okay, so Grattan says, oh, this is science. This guy is so great. So this whole theory that they have is based on the great Isaac Newton. Okay. How can we let go of a theory by the great Isaac Newton? It has to be right because Isaac Newton said it. So anyway, do you see my point there? Their whole theory of how they're approaching cosmology, the formation of the solar system, and all that is they've latched on to an idea that they can trace back to Isaac Newton, and because it came from Isaac Newton, therefore it has to be right. And I think this is similar to the business with Einstein and special relativity. They can trace it back to a great genius, and therefore it has to be right. And any contravening evidence, well, that can't be right. We have to ignore that because we have to support the great scientists of the past who have led us down this path. And so everything that they're doing has to agree with this idea that everything started out as a nebulous mass of gas, and then gravity, that powerful force of gravity, brought things together to form the masses, the stars and the planets. And that sounds really great, except for when they worked out the calculations, they found out that angular momentum doesn't really fit into their picture. So that's kind of where the problem is that we have with respect to angular momentum. Now, there's an interesting Armbart-Sumian, I think I mentioned him before. Victor Armbart-Sumian had this idea that the opposite occurs, which is somewhat similar to Vladimir's idea. And Armbart-Sumian proposed that stars originate from some kind of dense mother object. He's not very clear.
That was what I was thinking. That the gas clouds would have to have something to gravitate towards, such as Jupiter and Saturn, that they're supposedly gaseous. I mean, is there possibly a dense core, for instance?
Well, I'm going to talk a little bit about this book that I'm referring to was written around 1963, so this is pretty old. Okay, and Armbart-Sumian did his work in the 1950s, so his ideas were more current in the 1950s. I doubt if you even mentioned his name to a professional astronomer today, he would even know who you're talking about. Okay. So there's a paper in this book where where this E. Schatzman, who's a French guy, here it is, and he addresses this issue of he talks about star formation, and interestingly enough, he starts with Armbart-Sumian's idea first, merely to dispense with it as being anything that makes sense. So, in effect, basically, what these people do is they say, okay, let's look at this idea that things originated from stars and planets originated from dense matter, and so he uses an angular momentum argument to say that there would be too much angular momentum in this very dense star that would be the predecessor of, say, the planets. So the planets can't come from this dense object because there'd be too much angular momentum. And he sort of basically poo-poos the whole idea in the first part of his paper. And then he proceeds to explain why the idea of contracting of a gas cloud is the best idea, and he goes on for another 20 pages talking about that. So anyway, my point is, I think in science, people are too quick to dismiss ideas that they don't really like. The Armbart-Sumian idea that, which is the opposite of stars and planets originate from gas clouds, that's Newton. Interesting. I didn't realize that was Newton, and it may not be exactly that, he was that influential with this idea, but I think because they could find a paper or a letter where he says it, then they can trace their idea back to him, and they can kind of claim that they have the great heritage of Newton behind them. And then that idea was again taken up by Kant and Laplace. Once Kant and Laplace took up the idea of what's called the nebular hypothesis, that the solar system, the planets, the sun and the planets condense from this nebular cloud, okay? And then it sort of became dogma, and to a certain extent, but they still had this angular momentum problem that they couldn't really get rid of. And in the 1930s and 40s, there were a number of theories that were proposed. Weizsäcker came up with this one that there are these multiple vortexes in this nebular cloud thing. But they all assume that the nebula has to kind of come down and collapse down to form a spinning disk. And I've never really understood how it forms how a cloud of nebulous gas just kind of collapses down and forms a disk. And that never really made any sense to me. How does it form a disk? Well, you have to have a disk in order to essentially explain the orbits of the planets in a plane. Okay, so you have this ecliptic plane of the planets are all in relatively the same plane of motion, that they're rotating around the sun. So that means you have to have this idea of a disk, okay, or a flat object. So the cloud condenses down and it forms a kind of a spinning flat plate-like disk object. And then out of that, the planets are supposed to condense, okay, through some mysterious process, which I've never really been able to understand. You got a question there, Jerry?
Yeah. Well, I've often considered the I forget what it's called, ecliptic. I get it confused with ellipticals and such.
Ecliptic, I think, is the correct pronunciation.
Yeah, the plate type pattern that planets revolve around, but they'll line up. So, I mean, is there any explanation as to why that occurs?
Well, their explanation is that the cloud contracts down to form a flat disk that's rotating. But the problem is, where does the rotation come from that this cloud has? This cloud's supposed to be rotating around like a spinning plate. And where does this rotation come from? And how did the rotation originate? And so this is one of the big problems is, where does this angular momentum come from? If you assume there's no angular momentum to begin with, then how do you explain the angular momentum that exists that we measure of the planets going around the sun? But if you assume there's an angular momentum of the cloud to begin with, then there's too much angular momentum when the planets form. And all of it's in Jupiter, very little of it is in the sun. So then you also have another problem with why is more the angular momentum in the solar system in Jupiter than in the sun? Why does the sun have so little angular momentum? And so this is a big problem to explain.
In my work, the angular momentum is intrinsic to basic particles like electron and proton. So that's the electron and proton bit cycles is what I call them. And that was used to derive Planck's constant. That would be a proposal, anyway, to consider as to the origin of the angular momentum, that it's intrinsic in the particles that compose the universe.
I'm glad you said that because I hadn't thought about that. That's interesting to think about.
Well,
so
when we get to the binary mechanics cosmology up there in February, I'll go into some more detail on that. But certainly if the question is the origin of angular momentum, binary mechanics has a very specific answer, and it all checks out in terms of the calculations that I've done, which allow the derivation of Planck's constant, which has to do with the spin of the electron and proton, which is thought to be, the conventional people say that, well, it's really not spinning because it's a point particle. Or if it's a sphere, well, maybe it's spinning. In other words, there's no consistent answer there from your conventional physical literature. But in binary mechanics, the fact that we could actually derive the measured value of Planck's constant from first principles without any input from any other observed measurements of so-called fundamental constants is something to put on the table, at least as a possibility, I think.
Okay, I like that.
Well, thank you.
Jim, could I just ask, I was going to wait until your lecture. It's a very elementary question. Perhaps I should know the answer already, but because I've only dabbled into it. But where does the term binary, in modifying mechanics come from? What's the binary nature of it?
It has to do with full quantization of energy, space, and time. And we start with a basic cube of space, and that actually space would have a structure, okay? Now the binary comes in. Let's say we have one elementary volume, which is a size L, which is the primary length constant of binary mechanics, cube of space, okay? Now, if it could have more than one thing in it, then that really probably is not an elementary volume. We could subdivide it into two volumes because there's two things in there. So that if we're going to go full quantization, the whole concept would be that there's only two possibilities, something versus nothing. If you could have three things or four things in a particular volume, well, then that's not an elementary volume. You need to break it down more. So does that help? Does that conceptualization help, sir?
It does help me, yeah, because it's very.
That's where the binary comes from.
It's almost like
in other words,
one
you
or
can
a
only
zero.
have one thing. It's a elementary volume, or what I call a bit locus. An L-size cube of space can only have one thing in it, or nothing. That's the one state and the zero state, and there's your one-digit binary number.
Oh, okay, I think that might help others as well. Maybe when you come, just in a few words of introduction, it's useful. Because otherwise,
in other words, we don't say what things are.
Yes.
What are things like tables, glasses, trees, cars, us? Binary mechanics doesn't say what it is. Binary mechanics just says in an elementary volume of size L cube, which I call a bit locus, can have something in it or not have something in it. And there you get your binary nature of things. And when you have full quantization that I'm describing, there are certain consequences which are absolutely unavoidable. And so it gives a discipline to scientific thinking. You can't just say anything. The reverse idea, of course, is continuous space-time. And that's what I think the powers that be want everyone to believe in, because they know that's not going to work. And, like if you're a major power, like let's say, I'm going off on another tangent of what Harry was saying a few moments ago, if I may, for a moment, that if a great power like, say, the U.S. or the European Union or something wants other great powers to fall by the wayside and to be technologically behind, they have a motive to promote false theories like special relativity, okay? So that this explains why there's all of this literature and evidence contradicting special relativity and general relativity too, I might add. But in spite of all of that, we want to use our media, the fake science news, to promote the idea that these are valid theories so that competing nations, maybe Russia, maybe China, whoever, is going to be left by the wayside because these theories are known to fail. And so that therefore a competing nation will fail. So, that's how it all fits together in terms of why why these false theories like special relativity are promoted and allowed to are promoted in the mainstream science media.
That's interesting, but my theory is that's just arrogant ignorance.
I have a question, Jim. You had mentioned, I forget your terminology exactly, but you had mentioned that some increments or areas of space either don't contain a particle, for instance, or they contain them or they don't. The areas where they don't, is that empty space?
Well, it's a volume of space that is in the zero state. Okay.
Okay.
Yeah, it's a. I'm familiar with what you're talking about, Jim, because I have a friend of mine who's he was interested in this type of thinking. This computer. He was a computer scientist guy, and he wanted to think that way. It's either there or it's not there. It either exists or it doesn't exist. That binary thinking, yes or no. Is there an object in that place? Yes or no. Binary thinking, binary mechanics. It's like, did I get that right?
Yeah, and in fact, everything in our, all the technology that we're using is digital technology based upon binary numbers. And so the only place you're going to find these analog computing, which is, for example, based upon the theory that space and time are continuous and can be and position can be represented by real numbers and so forth and so on, is in the fantasy physics that they want to promote to be sure that anyone that believes in continuous space-time will, in the long run, be technologically behind because they don't have a useful theory that actually works.
But just a point about your earlier suggestions. I mean, it's not just the big, powerful nations who are promoting a lot of the science that we decry. The small nations, or you mentioned the opposing ones like Russia and China, they all promote special relativity and all these ideas that we decry. Is this lack of confidence, or it's an orthodoxy, And the other thing about what you said, Harry, about it was following on from our earlier discussion about not questioning, the authorities and so on. But when it comes, it comes with a crash. So in other words, Einstein, the papers in 1919, they say Newton is wrong. It's the biggest revolution that you can imagine. And now we have a new man, a new omniscient creature or infallible creature that you must believe instead of Newton.
Well, he has to be the smart, super brilliant guy in order to contradict what Newton said, because Newton is the great god of, So, to me, it's actually amazing that they went with Einstein. But what I find interesting is the quote where he says that he wanted to be cremated because he didn't want people to worship his bones. I don't know if you've heard this.
I haven't heard that.
I thought, when I read this, I thought that's the most arrogant thing I've ever seen.
Well, you see, Newton was actually debunked by Galileo. The small g acceleration due to gravity. That small g, leave out the word gravity and just say that there is an acceleration observed um, toward the center of the Earth and so forth. Um, Galileo actually showed with the Tower of Pisa that the different masses uh, fall and accelerate the same. And so he debunked Newton's universal theory of gravitation, which was pegged to the mass of the object even before Newton proposed it. And so, Newton completely ignored the result of Galileo, which showed that the mass of the object was not related to the acceleration observed, the small g. Okay, and so so Newton sort of threw out the most basic concepts that Galileo had served up to him on a silver platter.
Okay, on a different, let's get back to the angular momentum thing, which I'm kind of interested in because I thought maybe you might have something to say about this, Jeff. I'm wondering, how does this macroscopic, large-scale objects, how do they acquire angular momentum in binary mechanics?
Well, if each particle has an intrinsic angular momentum to it, then you add up the angular momentum of different particles, and you get the fact that the Earth spins, galaxies rotate, etc. Angular momentum, you can analyze it, and I did this with the proton and electron bit cycles as each element of angular momentum, and you can add, in the proton bit cycles, there's actually 42 locations, okay, that the one state quanta revolve around in a sort of a generally circular pattern. Okay, you can consider the angular momentum of each location and add it up to get the total, which gives you your Planck's constant h, divided by 2 pi, which is the 1/2 spin of the proton and the electron. And so I've done the calculations in several different ways in different papers and always come up with the same result. And so for larger assemblages of these particles, the angular momentum would add up in the same way. In other words, you can consider the total angular momentum of, say, a planet or a whole galaxy as the sum of the individual angular momentum contributions of each particle therein. And that's just conventional classic physics there.
Okay, well, anyway, I wanted to, we got a few minutes left here. Wanted to point out that one of the statements that you see almost universally is that every object in the universe is rotating. And it's this universality of angular momentum, I think, that is of interest to cosmologists and astronomers. And because everything's rotating, and of course, planets rotate about the sun rotates on it. You got to be careful about the word rotating, so I'm going to be careful about it. A planet revolves around the sun. The planet rotates on its axis, so we have to be careful about that. That was pretty sloppy when I said that. So there's revolution, which is going around an object that's at the center, and revolution is spinning on its axis. So
Rotation.
Yes, rotation. Rotation is spinning on the axis, and revolution is going around in an orbit. We need to be careful about that. But in this case, when we're talking about angular momentum, in most cases, we're talking about the object itself is spinning on its axis. And that's what you're talking about, right?
What I'm talking about?
Yeah, when you say angular momentum, you're talking about an object that's spinning on an axis, right?
Well, the energy quanta are spinning around the axis
Okay.
in an orbit
But you're
around
talking
the
about
axis.
rotation. You're talking about rotation.
Exactly.
Spinning or rotation.
Yeah, and
Not
that's angular
revolving,
momentum, and you can
not
add it up.
revolving around well, it could be, in your case, you could say it's both, because the energy is revolving around a central
Well, in
axis.
classical treatment of angular momentum, the total angular momentum of a large object like a planet or a galaxy is the sum of the angular momentum in the individual constituents of it.
Okay.
That's the classical notion. So and I use that classical notion,
All right.
and it works. The numbers come out right.
Well, I don't really have a whole lot more. I could have talked more about this subject. I didn't really have the time to really get into it. I did notice here that in the book, the new book that I got, a different approach to cosmology. He has in chapter 23 some unsolved problems. And of course, the first unsolved problem that they mention is the origin of angular momentum. That's how important it is. So it's
He hasn't read about biomechanics mechanics.
right.
He's at a real disadvantage there.
Well, I mean, I think it's not given the emphasis that it probably should be. And, we're arguing about Einstein's special theory of relativity, and all these guys are doing, spending all this money bouncing particles together and accelerators and all this other stuff. But it seems to me this is a bigger physical question, a lot philosophical, physical problem, than a lot. It's like buried down they're not really. There doesn't really seem to be much of an explanation of where angular momentum in the universe comes from. I guess Vladimir has an idea about that. He's got a theory about that.
Well, again, this social analysis that I was venturing on, which is dangerous territory, because I'm not really an expert in that. But you don't want possible, you see, correct theories could lead to technology that could have both economic and military implications. And the last thing you want is to be broadcasting correct scientific information, so that the whole media thrust is to support known wrong theories, and to be sure that you keep without publicity the real research that's being done.
So that's the mushroom theory.
I haven't heard that one, but it sounds good.
That's you keep them in the dark and you feed them shit.
Okay. Well, the longer people keep arguing about special relativity and general relativity, string theory with its umpteen different dimensions and all sorts of nonsense, the more the intellectual assets of a particular country are going to be occupied with that, and not doing real science, which is going to perhaps advance the country economically and or militarily, so that there's a definite motive to promote wrong theories and to keep them alive and have people arguing about them for forever. I mean, let's say a UFO was found in Roswell, for example. Do you want to just go out and say, well, we have this thing that led to fiber optic discoveries. We have this stuff that led to other discoveries about metals and materials and so forth, which could have economic and military implications. No, the last thing you want is for that to be known.
Well, we're just, I'm a retired electrical engineer, and by wasting my time talking about special relativity, I don't think really matters. It's not affecting the economy one way or the other. It's just keeping me entertained.
Right. As long as you're entertained, you're not trying to create new knowledge with new frontiers in science.
Well, I don't think
and I'm not talking about you personally, Harry. The general.
I understand your theory. I just I think it's more ignorance of arrogance. You know, they're right because they say so, and they know what the truth is because they know what the truth is. That's the people that you're dealing with because they're in charge. They've risen up to be, you know, the chancellor of some powerful university in a powerful, rich country, and so obviously anything that he thinks has to be correct. Because if it wasn't
I don't
correct,
dispute
he wouldn't be thinking
that, you know, as long as it keeps possible competing nations on the right track.
I understand your point of view. I think the real issue is that people who think like the person that I just described are everywhere in our country, here in the United States. And basically, because of them, we're in deep trouble. And of course, because they're in charge, they don't know that we're in deep trouble because they're ignorant, arrogant, stupid people. And when you let ignorant, arrogant, stupid people run your country, you're heading into oblivion.
I tend to agree with that, but the contrary view, which I think is nearer to Jim's, if I'm not misunderstanding it, is that those guys are not stupid and arrogant. They're actually very clever. They know that you're right, or that we're right, and they're just deliberately hiding the truth and saying, well, let's obfuscate the situation because we're making our country more powerful and we're getting kudos from it and so on and so forth. They're the contrary. They're very smart devils.
I would be really reassured if I thought that was gay. It was actually happening. That would reassure me. I'm not reassured at all.
Which is worse. Well, I think there's a little of that, but I think mainly is actually just groupthink and lack of ability to think for oneself and to be influenced by.
Well, Pat says they're just trained parrots.
Yeah. Have you ever heard of the Abilene paradox?
No.
Okay, I could give a talk on that sometime, but